Hello and welcome to a new video on journal bearings, a video that deals with the simplification of the Navier-Stokes equation and the solution of the simplified Navier-Stokes equation. Not only the solution, but also the integration constants that are involved in that solution will be determined. So everything about applying the Navier-Stokes equation to journal bearings is discussed in this video. So how can we simplify? I would say further simplify, because we already simplified the Navier-Stokes equation. We considered incompressible fluids and we neglected the inertia terms, and now we have a pressure gradient included and we have the viscosity included. And how can we simplify the pressure gradient and the viscosity components? That's the first question in that video. So let's have a look at the pressure gradient. Well, the pressure gradient is written here, and what we do, it's already shown here, we neglect the radial component of the pressure gradient. Why? Because the most important part is the change of the pressure, so the pressure gradient in circumferential direction. Recall that in circumferential direction you have that lubrication gap and you have the convergent part and the divergent part of the lubrication gap, and the pressure changes enormously, tremendously in that lubrication gap. So there's a large change of pressure in circumferential direction. In axial direction, well, we do not know exactly. We will have ambient pressure at both ends of the bearing, and in between there could be some pressure change. So let's keep that term, I would say. Yeah? However, in a radial direction, the radial direction is tiny, 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 tiny small. Why? Well, if you look at, again, at that figure of the shaft inside that bearing, then I exaggerated for the lubrication gap in that figure. Usually, the lubrication gap is really small, several microns, for example, in order to generate that pressure film. It's not such a tiny shaft and such a big journal bearing, but the shaft is approximately as large as the diameter, or as the radius. The diameter of the shaft is nearly as large as the diameter of the inner diameter of the bearing. So the radial direction, the free length, is really, really small, and the pressure has not much chance to change during that time. So therefore, we will assume that this change is equal to 0, and we just have two terms in the pressure gradient, and we have reduced the dependence of the pressure field on two quantities, namely on the circumferential direction phi and on the axial coordinate z. So the pressure field will be a field on two parameters, on two variables, the circumferential coordinate phi, and finally also z, the axial coordinate. So with this in mind, let's move to the viscosity terms. There's a lot more to do in the viscosity because there are so many terms. If you have a close look on the terms, then you see that they depend on different order of, on different powers of 1 divided by r. There are terms that are independent on 1 divided by r, there are terms that have a factor 1 divided by r, and there are other terms that have a factor of 1 divided by r squared. Same for the second line, same for the third line. So what can be said about the order of magnitude of these terms? Again, r, our radial coordinates, starts to run, well, from the value it has at the, well, outer outer limit of the shaft, so starting at the circumference of the shaft, and continues until it meets half the diameter of the bearing housing, so inner diameter of the bearing housing. So it starts already with a quite large value, and it doesn't change much. So what can be said about 1 divided by r? as r will be quite large, it will be at least of the order of magnitude of the radius of the shaft, perhaps a little bit larger, but not larger than half the diameter of the inner diameter of the bearing. So 1 divided by r is already small, 1 divided by r squared is even smaller, and then there are terms in 0 order of 1 divided by r. And what we retain is, in a first step, we just retain terms of 0th order in 1 divided by r. So which terms do we retain? The first ones here, they are all independent of 1 divided by r, and the terms in dv as second derivative with respect to z. All the other terms will be neglected. Well, there are terms in r squared and there are terms in 1 divided by r. And now there's a last question. Which term, if we have two in this equation, one is the second derivative with respect to r, the other is the second derivative with respect to z. Also for the other components, this holds. Which one is stronger? Which one is dominant? Or is there a term that is dominant? If yes, we can simplify even further and we just can retain one term. That makes then the solution easier because it's just integrating twice. So what do you think? Maybe you can discuss this. What is more important? The second order radial derivative or the second order axial derivative? Well, I give you the chance to stop the video here. So either you stop or you continue watching and discussing with me. Well, what happens in radial direction? In a radial direction, there is a tremendous change in velocity because at the inner diameter of the bearing, there will be a no-slip condition. That is, the fluid sticks to the bearing and the bearing is static. No velocity at all. At the shaft, at the circumference of the shaft, the velocity, the fluid also sticks to the shaft, so a no-slip condition in general, but the shaft rotates, so there is motion. And that velocity has to drop down during that tiny little distance in a radial direction. It has to drop down to 0. Therefore, you can assume that the second order derivative is quite large. In axial direction, there is not much flow. You do not push or pull your rotor in axial direction, and due to the stick of some fluid, there will be some kind of flow, but there will be sticking of fluid on the rotor, but the rotor will, in our case, as in machine dynamics, we will not consider axial bearings. There will be nearly no motion in axial direction. The fluid sticks, of course, also in axial direction to the bearing, and the relative velocity is then 0. Yeah? So not much effect in axial direction, but a lot of change, velocity change, in a radial direction, and therefore we will retain the second order velocity gradients in radial direction, and we will neglect the second order derivatives in axial direction. And this then leads just to the fact that we consider the first term as being dominant in all three equations. So now we are in place to formulate the simplified Navier-Stokes equations. And not only to formulate them, but also to solve them. You can see it's the balance between the pressure gradient on the left-hand side and the Laplacian multiplied by the viscosity on the right-hand side. And we retain from the Laplacian, as I said, just the first term, and we neglect here also the first term for the pressure gradient. Otherwise, no changes, except for one small one that I will do now. I will replace now, for sake of integrating here with respect to r, I will replace here the variable r by uppercase R, which is half the inner diameter of the bearing housing. And then integration is quite simple, because in every case the things on the left-hand side here is then a constant with respect to R. Keep in mind that the pressure does not depend on R anymore. Kicked off that dependence here. And then it's just the integration of that constant. And you know how that integration works. Oh, from engineering mechanics perhaps, but also from mathematics. It's well, a classical function with constant acceleration that you integrate twice. In the first case, it's even with constant velocity here. So you get a linear quantity in the radius for the velocity field in radial direction, and for the velocity field in circumferential and in axial direction, you get a leading term that is in R squared, and the coefficient then comes from these parts of the pressure gradient. And keep in mind that we replaced 1 divided by R by 1 divided by capital R. And as you can see, there are 6 integration constants here. 6 integration constants that we have to determine. So we have to formulate boundary conditions for the velocity, and we need for each component 2 boundary conditions. Well, 2 boundary conditions, but we have 2 boundaries at hand. Namely, one is the circumference of the shaft, the other one is at the bearing housing. And in both cases we have no slip conditions. However, for the bearing housing, they are quite simple, because the bearing housing is static, so it does not move. So the velocity components will vanish there. So they will vanish for R equal to capital R. And for the shaft, well, for the shaft we have 2 problems. The first one is the shaft will move. Yeah? So the no slip condition tells you that the velocity is the same as the velocity of that shaft, but the shaft is a rigid body, so it has a velocity field at that point at the circumference. And then you see something else. Where do I apply that boundary condition? Well, here it was clear it's capital R, half the inner diameter of the bearing housing. For the shaft it's not so clear, because the shaft is not located anymore with its geometric center identical with the center of the bearing housing, but that shaft inside that bearing is allowed to displace as a rigid body. So it's described by 2 displacement variables, by a radial displacement and by an inclination angle. And now from this we have to apply that boundary condition with respect to some, I call it as lowercase h, the lubrication gap. That's quite a complex problem, because you have to apply this boundary condition for well, any point on that boundary. So it's a velocity field here. So you have to compute this for any point at the circumference of the shaft. And this is the function h. So problem is not yet solved, but you see that due to these simplifications, the solution for the velocity field is now quite simple to obtain, but the computation of these integration constants is really quite involved and will govern the rest of this video here. Yeah? So in order to compute, to derive these boundary conditions, these integration variables, we have to determine 3 things. We have to determine the lubrication gap h, that function, which will be a function of the displacement of the shaft, which is described by E and gamma, by a radial distance and an inclination, and which is also a function of phi of the circumferential coordinate of your polar coordinates. And finally, we have to determine v sub r and v sub phi that also depend on phi and on the velocities of that rigid body, so on the radial velocity, on the circumferential velocity, and on the circumferential coordinate. Well, and this will be done next. Before I do this, before we derive these expressions, where we can just profit from the result and already replace the integration constant. So we can move one easy step further, and then we consider the difficult things, namely geometric considerations to compute the lubrication gap and the two velocities. So let's move a step further. These are the boundary conditions. Here are the solutions. Let's plug in the boundary conditions. Well, this can be formally done by replacing on the left-hand side and on the right-hand side. So replacing on the left-hand side the lowercase r by an uppercase r, and then equating this to 0 and to v sub r. It can be also done a little bit faster, right? By observing that, for example, in this case, we have a linear function. That linear function should be equal to 0 for capital R. It should be equal to v sub r for capital R minus h. What is the possibility? We set r minus capital R minus lowercase r divide by h, and then you can see that due to the fact we used that parenthesis capital R minus lowercase r, we are in place to guarantee this 0 here. And now in order to guarantee that we get a v sub r for lowercase r equal to capital R minus h, the parenthesis amounts to lowercase h. We have to divide by lowercase h and multiply by v sub r to satisfy the second boundary condition. So this would be, I think, the approach. Then some formal computations. You just look sharply at the expressions. You want to satisfy this 0 here, so you always need capital R minus lowercase r, and the rest is a manipulation of the leading factor from the other boundary condition. In more or less the same way, this works for the second part, with the tiny exception that we have an r squared here. So we need first an expression, that one here, that allows us to satisfy the right boundary condition here, and that vanishes for the other condition. And then we need a second order term, r squared, that will vanish on both boundaries. So if it vanishes on both boundaries, it must be composed by capital R minus lowercase r and by capital R minus h minus lowercase r. And the rest is just satisfaction of that coefficient. So the leading coefficient in r squared must be 1 divided by 2 mu r dp by d phi. And here it is, the solution without any integration constants. For the last component of the velocity vector, things are even easier because we have twice the 0 here. So we do not need such a linear term that takes care of the right boundary condition. The right boundary condition is 0. We just have to copy this term here, of course, with the appropriate leading factor. So 1 divided by 2 mu dp by dz. And that's it. Yeah? So let me recall what we have to determine now. We have to determine the lubrication gap h. We have to determine the two velocity components, the velocities of the velocity field of the shaft, v sub r and v sub phi, at the circumference of the shaft. That's the task. Okay. So then let's move to the lubrication gap and to some geometric exercise. This is the situation for the lubrication gap. So again, this is the center of your coordinate system. The center of the coordinate system is the geometric center of the bearing. We have the axes x and y in vertical direction and in lateral direction. There's a displacement of the geometric center of the shaft. This will be the center of the shaft, and that distance is, radial distance is e, and the angle is gamma. What we want to measure? We want to measure the lubrication gap at some circumferential position phi. This is the whole circumferential position phi until there. And you can see I can decompose this angle phi into the angle gamma, in which we have the displacement of the geometric center of the shaft and some additional angle, which is then called theta. In total, the lubrication gap depends on time and on phi, not on phi alone, but it depends on time. Why does it depend on time? Because the displacements of the shaft, namely that E is a function of time, and the gamma is also a function of time, because as the shaft rotates, maybe the center of the shaft also displaces. No? So these are time-dependent functions. So I can represent that dependence either by being a dependence on phi, E, and gamma, and keeping in mind that E and gamma are time-dependent. I could also write it as a function of phi and time t. So as a field quantity, I would represent it by phi and t. As a physical quantity, I would represent it by the dependence on E and on gamma also. So how do we compute that distance? Well, we have here a certain triangle that is included in that drawing. That triangle is obtained by connecting the center of the bearing with that point on the circumference, and then drawing from that point a line to M, and from M again back a line to the center of gravity. From the triangle, what we do know is we know that part, which is E. We know the length of the line from M to the circumference, because it's the radius of the shaft. And we also know that angle, which is, and you see it makes sense to introduce that angle, theta, because theta is just the difference of phi minus gamma. Gamma shall be given, the same as the E here. It must be provided by your rotor dynamic program. And the position at which we want to measure, or we want to determine that h, so the phi here shall be also given, or shall be set as a value, so variable. So what do we have to do? All we have to do is to obtain this length in the triangle. And therefore we split this triangle in two parts by introducing the height here, by producing the height from M to that line. And then we need these two projections, the left projection and the right projection. The left projection is quite easy to obtain, because we know in that now tiny little triangle, we know the hypotenusis, which is E, and we know the angle, that is theta, and the projection then on this line is then E times cosine theta. So we take the total length, which is capital R, and we deduce the length of these two lines in these two triangles. And the first one, so we take R, was E cosine of theta, which is phi minus gamma. And the second one, so the second triangle, is analyzed because we know the hypotenusis. We know that length, which is E sine theta. And then from the theorem of Pythagoras, we get the other length, which is then RW squared minus E squared sine squared theta. Okay. So again, it's remarked here that E of t is the eccentricity of the shaft center, and gamma of t the attitude or inclination angle of the shaft. Well, I could already stop here, but I don't like that equation in this way. It's written much more in a much more too complex way. First of all, what I would like to introduce here is the difference of capital R minus R sub W. So between the radius of the shaft and the radius of so half the inner diameter of the bearing housing. This is a very important quantity for journal bearings. It's called the clearance. So that can be easily done. I just subtract RW here, and then I add RW to that equation. And then I observe that this expression here also includes an R rw squared, and that rw squared, I would like to write it in, put it in front of that square root. So I have to divide the whole square root by rw squared and multiply then by rw squared. So this leads me to the following expression. First, minus rw, and the corresponding plus rw sits here. Yeah? And then I copy the term minus e cosine phi minus gamma. And for the root, you can observe that in the root I also take the rw squared out of the root. So it appears as here with the negative sign as minus r sub w in front of that parenthesis. So I have to replace this by 1, and I have to divide in the second term by r sub w squared, leading to e divided by r sub w squared. Why do I want to obtain this result with the e divided by r sub w squared? If you compare the magnitude of these two terms, then again, the displacement e is limited. If you displace more than the clearance c, then your shaft will hit the bearing housing, causing perhaps catastrophic failure, causing that the shaft rubs on the bearing housing, which is very, very unwanted. So the displacement E is limited. It's limited to C, to that clearance. C is much, much smaller than R sub W. It's just a part of that. So E divided by R sub W will be much smaller than 1, close to 0. The sign is bounded by 1. So the whole expression will never be larger than E divided by R sub W squared, and this is negligible when compared to the 1 here. So the whole term under that root, the radicand, can be replaced by 1. Taking the root of 1 is still 1, but then computing minus 1 plus 1 is 0. So the whole term in that parenthesis is approximately equal to 0. So we can drop everything here. The terrible root will be lost. And the final expression is quite simple. We introduce the clearance here for the difference, r minus r sub w, and the remaining term is minus e cosine phi minus gamma, or minus e cosine phi minus theta. Sorry. Yeah. Because E of t is much smaller than r sub w. Okay, first task is solved. We were able to compute the lubrication gap, and as you can see, we obtained that lubrication gap for any value of phi. So at any circumferential position, we are able to determine the gap size. Not only here, but also, if you like, opposite, everywhere, for every angle phi ranging from 0 to 2 pi. Given the values of E and gamma, the eccentricity and the attitude angle, which are obtained from the rotor dynamic program, which is, so to speak, not our task when we are dealing with journal bearings. That is the information that is provided by the rotor dynamic program. On the other hand, what you have to do, if you are responsible for the journal bearing module in that computational code, you have to provide the bearing forces, the restoring forces, back to the rotor dynamic program. And these bearing forces are obtained from the pressure field, from integration of the pressure field over the circumferential direction and the axial direction. And therefore, we derive the Reynolds equation and we want to solve it in order to get the restoring force. So let's move to the two velocities that are missing. So what can be said for the velocity field? Well, the velocity field at any point at the circumference is given by the velocity field at point M. And then you would have to take the vector product of the rotational velocity with the position vector from M to the corresponding point on the circumference of the shaft. So let's plug in here for these vectors adequate quantities. What do we have? Well, we represent the velocity at the circumference of the shaft by its Cartesian coordinates, v sub x, v sub y, and 0 because we do not move the shaft in axial direction. We represent our rotational velocity by 0, 0, and thus just the rotation around the z-axis, which is the axis of rotation. And we represent the position vector by r omega. And now, if you look at these angles, then we measure from a parallel to the vertical axis here by alpha 2. We measure that angle, but we take sine pi divided by 2 minus alpha 2, which is then just the opposite, so the missing part to the horizontal direction here. And from this we take the sine component and the corresponding cosine component to determine here that point. And the length of that vector is then r sub w. Okay. What else do we need? There's one thing missing. We need the velocity of the center of the shaft, which is just the velocity that should be obtained or should be able to be computed from the information from the rotor dynamic program, namely from the radial displacement and from the circumferential displacement. Indeed, we have to take the time derivative of E cosine gamma and E sine gamma, which is the projection of the radial displacements and the circumferential displacement, so from the displacement on point M in the Cartesian directions in x and y direction. You can see the projection on the x-axis is E cosine gamma, the projection on the y-axis is E sine gamma. So this time derivative has to be taken, and we have to compute omega times r. This is done here. It is omega r sub w, and then for the vector product you obtain minus cosine pi divided by 2 minus alpha 2 and sine pi divided by 2 minus alpha 2. Now there is some more computation necessary, because you can see that this angle alpha 2, well, is nice, but maybe it's better to work with the angle alpha and to express everything by considering again that triangle here. So let's analyze that situation. The angle alpha 1, which is obtained from alpha 2 by deducing here, as you can see, it's the angle gamma that is involved here. There is just pi divided by 2 minus alpha 2 is equal to pi divided by 2 minus alpha 1 plus gamma, or alpha 2 is equal to alpha 1 plus gamma. Yeah? So that angle alpha 1 now forms, together with the two angles in the triangle close to that height here, b sub 1 and b sub 2, it just forms an angle of 180 degrees, so of pi. So alpha 1 is equal to pi minus beta 1 minus beta 2. But it's possible to determine these two angles adjacent to the height in the triangle beta sub 1 and beta sub 2, because we perfectly know these two triangles. That has been seen from the study of the lubrication gap. So for b sub 1 we obtain a result, the b sub 1 being that angle here. It's just we take the height, which is E sine phi minus gamma, and we take that hypotenusis r sub w, and then minus r cosine of that expression is equal to the angle beta 1. Well, and for beta 2 in the other triangle, where we know perfectly that angle, it's theta, we know the second angle in the triangle, which is a 90-degree angle. So that's the height. So therefore, the height must be orthogonal to this line. And then we just have minus pi divided by 2 minus theta, and theta was phi minus gamma. Okay. Well, if you look again at the lubrication gap, then what you will observe is that E sine phi minus gamma, keep in mind it was C minus E cosine phi minus gamma, is just the derivative, what stands here, of the lubrication gap by phi, the partial derivative of the lubrication gap by phi. Therefore, in the R cosine function, we can replace the expression by 1 divided by RW dH by d phi. So this E sine phi minus gamma is dH by d phi. There is a second manipulation I did here. You see that I have here a term of minus pi divided by 2. I've got a pi here. So pi minus pi divided by 2 yields pi divided by 2. Yeah? So this would be the expression for alpha 1. Now we move back to alpha 2. We have pi divided by 2 minus alpha 2 in the sine and cosine function of the last slide, if you remember well, in the position vector. So pi divided by 2 minus alpha 2 is then pi divided by 2 minus alpha 1 plus gamma. The result for alpha 1 is here. Good to see that it also starts with a pi divided by 2, and we have pi divided by 2 minus alpha 1 here, and that we have a plus gamma, but in the expression for alpha 1 a minus gamma. So it seems that many of these terms will go away, and we just have beta 1 minus phi for that argument of the angles pi divided by 2 minus alpha 2. So it's beta 1 minus phi. And beta 1 is that R cosine of 1 divided by R sub W dH by d phi. Okay. Well, now we insert all these results and we formulate then the velocity vector in Cartesian coordinates, and then we have to transform it, of course, to polar coordinates. Yeah? Okay, so let me summarize the result. The first one was from the slide before the last slide. So we have a Vx and V sub y, the Cartesian coordinates. For the center point, we have to take the derivative with respect to time of E cosine gamma and E sine gamma. And from the vector product, we obtain omega R sub W minus cosine pi divided by 2 minus alpha 2 sine pi divided by 2 minus alpha 2. And for that angle, for that argument of the sine and cosine function we found on the last slide, pi divided by 2 minus alpha 2 is equal to that angle beta 1 minus phi, and beta 1 is the R cosine of 1 divided by R sub W and the derivative of the lubrication gap with respect to phi. So in Cartesian coordinates, we plug in everything we find by taking here the derivative with respect to time, that it's E dot cosine gamma minus E gamma dot sine gamma. So keep in mind that both E and gamma are time dependent. In the second row, we find E dot sine gamma plus E gamma dot cosine gamma. For the second term here, we insert our result, and to keep the result short, I just inserted beta 1, and as you can see, so beta 1 minus phi, and not replaced beta 1 by that lengthy expression. So what you can see is you would get, by inserting this, beta 1 minus phi. And then I changed the sign in that expression. If you switch the sign of the argument of a cosine, then the cosine will not change its sign due to its symmetry. However, the sine function will change its sign to a negative 1. Yeah? So therefore, it's minus sine phi minus beta 1 minus cosine phi minus beta 1. And now the transformation to polar coordinates is we have a v sub r is v sub x cosine phi plus v sub y sine phi. V sub phi is equal to minus v sub x sine phi, v sub y cosine phi, with the famous equations for the unit base vectors. This result can be obtained. So let's see what we get for the circumferential and for the radial direction. Maybe I start with the circumferential direction. Do you have a guess what you would like to obtain in circumferential direction? Well, if you think of some kind of rotational motion on a circle, classical result, you would like to obtain omega times r. Which r would here be appropriate? We are dealing with the circumference of the shaft, so it's r sub w. So a result at least close to omega times r sub w would be something you would expect in the circumferential direction. Let's have a look whether this is true. So this is again the result now in Cartesian coordinates. And now this was the projection on the circumferential direction. Well, obviously we have to do here some manipulations. The first one is, well, we neglect the translatoric part for the circumferential direction and I have only the rotatoric part. Why? Well, the translatoric part stems from the movement of the center of the shaft, that rigid body motion. That might be there, but it's limited. It's limited in this amount because you cannot move much with that E, for example. On the other hand, the rotation of the rotor, I'm not talking about the center of shaft, that gamma dot here, but I talk about that omega, will be really, really large. Well, if you use a classical rotor, then you have a lot of rotations per minute or per second or whatsoever. So the rotational part will be much more larger than the translatoric part. So first we neglect this part. This brings us closer to a result of omega times r, right? Then we have to multiply, if you look then at the expression, you have to multiply this function by a sine phi and the second one by a cosine phi. Well, we are not yet there, you would say. It's still not omega times r sub w, but beta 1, keep in mind, it was something like dh by d phi, 1 divided by r sub w. If we take the angle beta 1, so it was the arcus cosine, the argument, so beta 1 to be close to 90 degrees, then what you get is a v sub phi is approximately omega times r sub w. And this is the result I will work with here, with that approximation. So in circumferential direction, approximately, we get omega times r sub w. You could say, well, you can obtain this result just by guessing without doing all the computations, but from the computations and the simplifications, I guess you get a little bit more insight into this result. So let's move to the radial direction, and there we cannot do at least all these simplifications here. So in radial direction, the formula for the velocity is the v sub x cosine phi plus v sub y sine phi. Well, we have here a translatory part, which consists of e dot cosine gamma minus e gamma dot sine gamma cosine phi plus e dot sine gamma plus e gamma dot cosine gamma sine phi. And well, it might be astonishing, but if you do the computation with the lubrication gap, you take the derivative with respect to time, taking into account, of course, the time dependence of E and of gamma here, then you arrive at this expression. So the translatoric part can be abbreviated by minus the partial derivative of the lubrication gap with respect to time. So the translatoric part of the radial velocity tells you something about the change of the lubrication gap with respect to time. And now the rotatory part. Well, for the rotatory part, so the last expression, we also take minus r sub w omega cosine phi minus beta 1 times cosine phi and plus sine phi minus beta 1 times sine phi. You can see that the negative sign here from these two terms moved at the first position. Well, we can simplify this result by applying the classical addition theorems for the product of cosine and sine function to yield minus r sub w omega cosine beta. But this is nice, because for beta 1 we had an arc cosine expression, namely 1 divided by r sub w dh by d phi. So let's plug it in here. And now we get an understanding of what happens in radial direction. For the translatory part, it's the change of the lubrication gap with respect to time. For the rotatory part, it's the change of the lubrication gap in circumferential direction multiplied by 1 divided by r sub w. And for r sub w omega, I inserted here, or abbreviated this expression by our approximation of the velocity in circumferential direction. And just a remark, in the following we will further simplify this expression and do not make a difference between 1 divided by r sub w, the radius of the shaft, and the half inner diameter of the bearing housing when it comes to this r sub w here, because the clearance is in general very, very small. So in the following, I will set r sub w is approximately equal to r and replace or drops the index w here. Okay, now we have all the results. We obtained already the solution of the Navier-Stokes equation and inserted the boundary conditions, so moved away all the integration constants in a general format. Then we saw that we have 3 parameters to determine, namely a geometric quantity, the lubrication gap, and 2 kinematic quantities, namely the velocity at the shaft circumference in radial direction and in circumferential direction for any material point that sits at the circumference of the shaft. And the results can be found here. For the radial direction, for the circumferential direction, it's just omega times r sub w, or omega times r, with this simplification. And now we have to go back to the continuity equation, insert everything in the continuity equation, and then we have the Reynolds equation. And this is done in the next video. So thank you for watching. See you again in the next video when I will show you how to finally derive the Reynolds equation from this result that is plugged into an averaged continuity equation. Thanks for watching.